the temperature sensor interfacing with microcontroller. For that we require the A to D conversion. We have seen different temperature sensors available in the market that we can select as per our requirement. Then we have seen the thermistor, whose output is in terms of the resistance. Then we have seen the LM34, which gives the output in 10 millivolt per Fahrenheit, and LM35 gives the 10 millivolt per degree Celsius. We can choose as per our requirement. So temperature is 0 degree Celsius, Vm will be 0 degree Celsius, 0 millivolt, and output will be 0. As we have seen, this LM35 gives the 10 millivolt per degree Celsius. If temperature is 1 degree Celsius, output we will be getting will be 10 millivolt, and accordingly bit pattern will be 1. So in this way we can calibrate the temperature for the displaying purpose on the LCD. So this is direct 1 10 millivolt, 1 2 20 millivolt, 2 is the bit pattern or the converted digital data from the ADC. So it is directly we can display it on the display device. Then we have seen what is signal conditioning and what is required to do for the signal conditioning. Need for the signal conditioning. Then we have seen the LM35 series, which gives the output directly 10 millivolt. It need not require any calibration. Then we have seen one example, that is interfacing of LM35 through ADC0804 to interface it with the 8051 microcontroller. We have seen the hardware. Here we are connecting LM35 to the ADC VN pin. Then we have understood the complete hardware description between the LM35 with ADC and from ADC to 51. Then we have written the program. First we have declared the hardware description. Then we have started program that we have made the particular port and pin as an input, from where we are taking data from ADC to 8051 microcontroller. That is giving the start of conversion signal with WR pin, then waiting for end of conversion through this INTR pin or P2.7 pin. When conversion is completed, activate RD bar to tell ADC to give the data or make the data available of D0 to D7 pin, so that we can collect it from the port. So converted data will be available on the port. We have to take into the microcontroller with MOV A, P1. Then we can convert it into the ASCII and we can display it on the display device. Clear? Set B RD for the next round to request the ADC to give the data. Do it continuously with SJMP. So this is all about we have seen for the interfacing of the LM35 temperature sensor with 8051 microcontroller, which requires the ADC in between. So today we are going to see next concept of interfacing, that interfacing of DAC, that is the digital to analog converter interfacing. Here I am. Remember the course objective, so that we have to achieve the outcomes. We are at principles of interfacing and programming stage, and today we are going to see DAC, that is the digital to analog conversion. Again we are with the data acquisition system, and we need to understand the role of DAC. In previous lecture with temperature sensor, we have seen that we take the temperature into the microcontroller through ADC. For that we require to analog to digital conversion. But sometimes we again require the signal into analog form. For that we need this digital to analog conversion. So today we are going to see details of this digital to analog conversion. Here we can understand the cycle. We are taking the real world data through transducer from analog interface circuits. We are converting it into the ADC. It will be into the microcontroller, and from microcontroller to give it to the real world, again we require this DAC, digital to analog conversion, which will be activated by means of the mechanical signal, electrical signal, thermal signal, sound, light. This is one example where we have taken sound as a signal, which gives the complete cycle, that is from sound to sound form, original taking from sound form to giving it back again into the sound form. So here is the digital to analog conversion DAC and its application as a sound. So sound we can take into the microcontroller or digital system through the sensor microphone. Microphone converts this sound into the electrical signals, and then with ADC we convert it into a digital form, which processes it with help of the processor, is the digital system. Then when we require to give it again into the sound form, we require this DAC. So DAC converts this electrical signal again into the sound form, and we have it available in the sound form. So here we can demonstrate the need of DAC. Here we can see the form of signal. This is the analog converted into digital form, and with DAC. This is the ADC, which gives the digital, and for DAC here is the output, again hit into the analog form. So here is the concept of DAC, exactly reverse of ADC. For ADC we have here a single channel which gives the 8 data bits. For DAC input is the 8 data bits and there is a single output. So this is the n bit DAC. Here is the graph which is exactly reverse of the ADC. Here it is now the digital input and the output is the analog. In ADC we have seen here is the full scale input voltage, and here we were getting the digital output. So here is the same concept of the quantization, and accordingly we get the analog output out of the digital. How to get the digital output converted into analog? For that we are going to use this formula. V0 is equal to V reference and the whatever bit pattern upon the 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 4, 5, 6, 7, 8. As I 2 raised to 8 we get 256. So D0, D7, D1, D2, D3 up to D7 are the bits. Whatever the position of bit 0, 1 we will be putting here, and to the denominator it is the 2 raised to 1, first bit 2 raised to 1, second bit 2 raised to 2, third bit 2 raised to 3, fourth bit 2 raised to 4, likewise 2 raised to 7 we get 2 raised to 8, 256 we get. Let us understand it with one example. If the data is 0, 0, output voltage of DAC will be all 0, because this all will be 0. Anything divided by 0 will be 0, we will be getting the output 0. Let us assume that V reference is 10 volt. So this is for the all 0 bit. Let us change the bit pattern. If bit pattern is 80 volt, bit pattern is 80H, so 1 0 0 0. So with this we will be getting 1 by 2 into 10, that is the 5 volt. Calculate the output of DAC if the data is FF. This is assignment for you, solve it. Let us understand DAC 0808 that we are going to use. Here is the pin configuration of DAC 0808. Let us understand the purpose of pin. One is not connected, second is the ground, third is the VEE will be ground. This is the output pin where we will be getting the analog output, and this A1, A2 to A8 are the digital pin where we are connecting the output of microcontroller, where we are getting the digital out of this 8 bit of the digital. Here is the LSB, here is the MSB. Take care while interfacing this pin. 13 is VCC, 14 is V reference plus. This is important pin for us as output of the DAC, that is analog voltage, depends on this V reference plus that we have seen in the previous formula. This is V reference minus and the compensation. Here is the chip that looks at actual when we will be developing our actual circuit. Pin description: 1 not connected, GD ground, VEE negative power supply, IO output signal pin. A1 to A8 are the pins of the where digital input can be connected. Take care of the LSB and MSB. VCC is the positive power supply, V reference plus positive reference voltage, V reference minus is negative reference voltage. Compensation capacitor pin we are going to connect over here. Let us understand the specification of this DAC 0808. This is 8-bit parallel digital data input. Fast settling time typically 150 nanosecond. Relative accuracy is at 0.19%. Maximum error we can get. Full scale current match is plus minus 1 LSB. Non-inverting digital input are TTL and CMOS compatible, so we can interface it easily with 8051 microcontroller. High speed multiplying input slew rate 8 milliampere per microsecond. Power supply voltage range is plus minus 4.5 volt to plus minus 18 volt. Low power consumption, that is up to 33 milliwatt at the rate when we are using the 5 volt. So it will be varying as per the input voltage. For 5 volt it is 33 milliwatt. Maximum power dissipation is the 1000 milliwatt. Operating temperature range is 0 degree Celsius to 75 degree Celsius. It can withstand with this range of temperature. So these are the specification of the DAC 0808 that we are going to use. Interfacing with 8051 microcontroller. Interfacing is very easy. Simple communication between the 8051 microcontroller and the DAC. We are getting the digital data out of this 8051 microcontroller through any of the port. Here we have taken port P1. So connect port P1 pins, that is P1.0 to P1.7 to the DAC pins D0 to D7, where we will be getting the digital data that is need to be converted into the analog, and converted data is available at this pin out. So data is in the form of current. We have to convert it into the voltage by means of this amplifier circuit, which converts it into the current to voltage. So this is the current to voltage circuit, and then we will be getting the output voltage which will be displaying on the scope. The rest of the importance of pin we have right now discussed. This is the V reference, VCC, this is the RD, WR, this pin we not required. Now we require only D0 to D7 pin and the output signal, and this is the V reference. V reference minus we have grounded, V reference plus we have connected to 5 volt. For output voltage we will be getting this output voltage directly in the form V0 to V reference, that is the significance of V reference, and the whatever analog bit pattern or digital bit pattern D0 to D7 we will be getting the output voltage that we have illustrated in the previous slide. Write a program. So analog signal may be available in the different form. We will be studying one by one form. First form is the square wave. So to generate a square wave, how is the program? For positive cycle, we will be taking the FF, or we are sending FF to the port P1, and for negative of the half cycle, we will be sending 0 0. So here should be the 0 0 for positive half cycle FF, for negative half cycle 0 0. So in this way the waveform will be displayed. When we are sending FF to the port 1, we get this positive peak. When we will sending 0 0 to port 1, we will getting the negative, and in this way we are doing it continuously with the SJMP instruction. In between we are taking some time delay to display this portion. So in this way we will be generating the square wave on the scope. Next is the ramp. How ramp look like? In this way. So accordingly you can decide the program logic to develop a ramp. What we have to do? We have to start from the 0. Continuously we have to go on incrementing. When it reaches to peak, we have to make it 0. In this way we can display the ramp waveform. Accordingly discuss the program now. Starting with memory location 0. Starting point is 0, that's why we have taken 0 into the accumulator and send it to the port. So we are at this particular position. With INC A, we are starting incrementing the count of accumulator bit by bit, and we will be displaying it to the port. We will be doing this unless it goes to peak, that is the position FF. That's why we have written the instruction CJNEA, hash 0 FF, means accumulator will go on incrementing and it is comparing with the FF, and if it is not FF, it will doing again incrementing, sending it to the port, incrementing and sending it to the port. So with this we are getting displayed this portion of the RAM. So when it goes at FF, accumulator content will be FF, then will come out of this loop and will making accumulator 0 and sending it to the port. So by making it 0, will be coming here again. So move A, 0 0 SJMP again, sending this 0 0 to port 1. So this portion will be displayed on the scope and we are doing it continuously. So this is the way that program can be written to generate a RAM on the scope. Next is a triangular wave. Understand the logic of displaying the triangular wave. Starting same like the RAM, from the 0 position, we will be incrementing contents of the accumulator by 1, simultaneously displaying on the port. We will be doing it till we reaches to peak, that is the FF. So once we reach to the FF, we have to start decrementing the accumulator till it goes 0. So in this way we will be generating the triangular wave. Let us write the program with this logic. CLR-A, where this position, display this position on the port and hence on the scope. INC-A, start taking this portion, go till this FF, CJNE-A, FF, compare till we get the FF and simultaneously display it on the port A. Once we go to the FF, start decrementing with DCA-A instruction. Now accumulator starts decrementing. Start displaying this onto the port and we will be getting this portion. So when we goes to the 0 with CJNE-A, do it again till we get 0. Once we go to the 0, we will again starting that, moving it into the accumulator and incrementing one, so that we can get the display. So in this way we will be getting this triangular wave continuously. Next is the sine wave. So let us understand the logic of sine wave to be generated. So we are not getting very smooth curve, we will be getting like this. To generate a sine wave, a table gives the magnitude of the sine angles between 0 to 360 degree angles. V out of the DAC for various sine degrees is calculated as 2.5 volt plus 2.5 volt into the sine theta. Let us understand this table. Here is the calculation done with this particular formula. This is the angle theta. This is the calculation of sine theta, and here is the V out calculated with the formula that we have seen in the previous slide, and these are the values to the DAC. So here is the complete table, and we will be writing program now. We have taken a lookup table, some memory location, given the label as table, where we have kept all the data we have computed with the previous slide here, starting from the 32 ending with the 32. So we have taken it in the steps, we have not taken the complete values. If we take all this complete value, we can get a smooth sine wave, but for writing a program we have taken some sample values. So 32 starting with the positive, and last 32 will be again coming to the cycle. So for complete cycle, this is the range of the values that we have kept into the lookup table. How we have calculated this value, that we have discussed in the previous slides. Let us write the program. Move R2 comma hash 25H. Why 25H? We have taken only 25 values. Whatever values we take to display a sine wave, the counter we have to take accordingly for that values. So here we have taken 25 values, so we have taken the count of 25 and R2 initialized as a counter for this 25. Next, in DPTR we are getting the address of this memory location labeled by name table. That's why move DPTR comma hash table will be giving the memory location into the DPTR. CLR A, make the accumulator clear 0, so that we will get this memory location. With move C A comma @ A plus DPTR. In DPTR we are having this memory location. In accumulator is 0, so we are at this particular memory location where 32 is kept. So take that into the accumulator, and from accumulator into the port 2. So port 2 is connected to the DAC, and DAC will be given the analog signal related to this particular data. Call delay INC DPTR. With INC DPTR will be here with the next byte. Do it continuously for 25 values, taking it from the lookup table, sending it to the accumulator, and from accumulator to the port 2, from port 2 to the DAC, and from DAC to the scope that is connected. So do it continuously for 25 values. We will be getting the sine wave as per the previous discussion. And here is the small delay routine is written to take some time to display the data. So one R1 counter is taken and it is decremented so that microcontroller get time, and during that time the DAC displays the data on the scope. So this is all about the sine wave generation and the use of DAC for generating a different waveform or generating a different analog signal. Thank you.